Firefighting used to consist of passing water buckets hand to hand. The first fire hoses of the 1600s were made of leather. But these hoses were heavy, would crack when dry, and often break open under pressure. Modern firefighting began with the lightweight cotton fire hose, lined with rubber to keep the cotton dry and flexible. Fire hoses come in a range of sizes to fulfill a range of functions, from small, lightweight ones for fighting forest fires to large, heavy-duty hoses for industrial fires. Production begins with hundreds of bobbins of polyester yarn, feeding automated looms a floor above. A series of spring rods keeps the yarns under uniform tension. This is essential to create a tight weave. The factory programs each loom to weave specific patterns which incorporate identifier stripes. This is a visual guide to help workers assemble the fire hose later on. This woven fabric will form the fire hose's exterior called the jacket. It's got to weather some nasty conditions, so they soak it in a plastic polymer solution with dye for color. The liquid encapsulates the fibers, making them durable and water-resistant. At another station, they mix granules of polyurethane, a form of plastic, with white colorant and adhesive pellets. This mixture is for making the waterproof tubing that forms the inside of the fire hose. When they activate the adhesive in the mixture with heat, this tubing will bond to the hose jacket fabric. The mixer feeds the ingredients to an extruder, which melts the mixture and forms it into a hollow tube. The tube then passes through a basin of cool water to set the plastic. Next, the tube goes to the inspection table, where an automated printer prints code numbers on it for tracking purposes. To assemble the fire hose, they first pull out an outer hose jacket over a 33-yard long cable. Then, with another cable, they feed a second untreated hose jacket inside the first one. Finally, they attach a cable to the third and innermost layer, the tube, and pull it along the entire length of the double jacket. Once it's all the way through, they trim both ends. The three layers, outer jacket, inner jacket, and tube, are now ready to become one. They begin the fusing process by clamping one end of the assembled hose to a steam nozzle. As the clamp holds the hose steady, the nozzle blasts pressurized steam into the tube. At the same time, it moves backward, pulling out any kinks. The hot steam melts the adhesive in the tube material, and it penetrates the inner jacket around it. Once everything's perfectly straight, they pump in cold air to solidify the adhesive. This permanently bonds the layers. They roll up the finished hose into a coil, controlling the winder with a foot pedal. Then they lay the coiled hose on a table to install the couplings. Those are the components that attach the hose to the water supply on one end and to the spray nozzle on the other. They trim each end and then insert a brass expansion ring and then an aluminum coupling on top. An expansion machine does the rest. They attach the end securely to the machine's protruding bar. Then the bar retracts and expands, pushing the brass ring outward. The force wedges the brass into the aluminum coupling permanently. This company tests every fire hose it produces under high pressure on this table. After marking the type of hose with a stencil and indelible ink, they fill the hose with water. They check for holes and kinks and verify that the couplings stay in place. After the test, they drain the water. They insert a giant sponge to get rid of any water left behind. And now these new hoses are ready for their baptism by fire. Precision tools that perform their task with split-second speed and accuracy are key in jobs where time is of the essence. Take, for example, the nozzle at the end of a firefighting hose. It allows a firefighter to regulate the pressure of the water exiting the hose, no matter how confined or widespread the flames. A fire hose nozzle isn't a simple point-and-shoot device. It enables firefighters to tailor their tactics by firing water in a stream or flush. Production begins with a long aluminum tube. A saw slices off 6-inch pieces called blanks. Just one tube makes about 46 blanks. A robotic arm swoops down to transport them to a lathe. Cutting tools form the valve body, which controls the flow of water. Then they rough up the surface, making it easier to grip. They make a ball groove on the outside rim for attaching the hose coupling. Next, they form the interior. Technicians verify the inside shaping with computer imaging software. It's on to the milling process. A computer-guided drill bores several holes for the nozzle and grip attachments. Coolant washes away the metal chips and keeps the drill bit from overheating. The transformation from a blank to valve body is structurally complete. A laser now engraves the flow indication. Workers install rubber O-rings on a mandrel shaped like the valve body interior. The rings keep water from leaking out the side of the nozzle. They position the valve body over the mandrel and blow the rings into place with a blast of air. Automated machines now mate the valve body to the nozzle's handle. A heated mold melts granulated rubber and casts it into ridges at the top of a rubber cylinder. This makes the shaper, the nozzle's adjustable head that switches the water from a wide spray to a narrow stream. Workers snip off any excess rubber, then ensure the rubber is solidly molded. Next, they apply grease to the inside to lubricate the parts and prevent corrosion. 2 more O-rings are inserted to keep water from leaking out under the shaper. Using a specially designed spoon, they scoop up tiny plastic ball bearings and drop them into a groove in the shaper. These allow the shaper to rotate easily. The shaper then goes over a barrel, a metal tube that helps form the stream of water. To attach it, they apply an adhesive to the threads on the shaper's base, then slide the part into place. Workers insert a pair of hard plastic balls into the shaper. These enable the shaper to glide back and forth on the barrel to shape the water stream. Now it's time to build the sub-baffle, the nozzle component that controls water pressure. First, they insert a pressure regulation spring into the baffle body. Then snap on a knob which changes between standard water pressure and low pressure. The whole device slides directly into the barrel. On the other end of the barrel, they screw on the valve body. A rotating wheel simplifies this process. They now affix a pistol-style grip. Finally, the gasket grabber goes in. The steel screen keeps out nozzle clogging debris coming from the hose. With the nozzle assembly now complete, it's time for what they call a damp run. Workers check everything to ensure the nozzle performs its tasks at every twist and turn. From the old-fashioned nozzle to the modern variety that comes in an assortment of flows, pressures, and sizes, the evolution of the fire hose nozzle is undoubtedly a lifesaver. Firefighters need boots they can pull on lightning fast to get to the blaze as quickly as possible. Those boots have to be fire resistant and waterproof. They have to provide good grip for climbing ladders and be sturdy enough not to puncture when stepping through sharp debris. Firefighter boots start out as a chunky block of rubber. The first step is to put the block through a mill. It passes through the rollers over and over again until it gradually flattens and thins out. Workers then add chemicals, anywhere from 15 to 35 different types, depending on the model of boot they're making. The rubber formulation is what makes the boot fire resistant. Once the rubber is smooth and malleable, about the consistency of modeling dough, they form it into sheets from which they'll cut the various pieces that make up the boot. They feed this sheet through rollers that imprint vertical lines on the rubber. They'll cut the sheet along these lines to make the strips that run down the back of the boot. From another sheet of rubber using a handheld die, they cut one layer of the multi-layered sole. They run an extra thick sheet of rubber through rollers that imprint a tread pattern. Then workers cut out the bottom soles. They mark the boot size on the bottom. Using yellow rubber, they cut out the boot's toe cap covers. The boot's leg has a stiff lining to prevent it from wobbling. Workers cut it from a rubber-backed cotton fabric following a pattern. Once all the pieces are cut, workers can assemble the boot on a form. They start with the lining, wrapping it around the front and gluing it closed at the back. Then they glue on the insole. For this model, it's made of rubber-backed felt. They secure the lining seam and seal it with one of those rubber strips we saw earlier. Now the vamp, a piece of felt reinforced with a thin layer of rubber. This gives the boot strength. Next, a toe cap sponge, made of rubber compounds. When they cure the boot, the sponge will inflate and hold this steel toe cap in place. To protect the firefighter's feet when walking through sharp debris, they add a steel arch and a steel sole. Next, an adhesive-back toe cap cover. Then a felt sole to protect the firefighter's foot against heat. It has a steel arch for stability, useful when the firefighter needs to climb a ladder. After applying a rubber heel reinforcement, they cover the lower part of the boot with yellow foam for insulation. They secure it using a strip of rubber. Now they finish the bottom of the boot in black rubber. They reinforce the back and sides in yellow rubber and finish them off in black rubber. Next comes the yellow toe cap. Then a rubber pad to protect the front of the boot when it rubs against the rungs of the ladder. Now the bottom sole. They use a press to seal it in place. Rubber bonds to rubber under pressure. They apply a rubber trim around the bottom using a small roller to press it in place. Workers then press all the seams to ensure they're well adhered. Then it's into a vacuum machine for about 4 seconds to create an airtight bond. Finally, the boots go into a giant oven that heats them to 280 degrees Fahrenheit. An hour and 45 minutes later, the rubber is cured and hardened, and all the pieces have fused together. These boots are ready to take the heat. In the early 1800s, luggage maker Henry Gradicap created one of the first firefighter hats. The leather helmet had a long rear brim and curved sides as a shield against falling debris and water running down the neck. Except for a few high-tech additions, this basic design is still used today. Leather is surprisingly flame-resistant. When reinforced, it also becomes a remarkable hard hat, protecting from heat, liquids, and sudden impact. On this newer model, the accessories shield the eyes and ears too. A helmet starts with 4 die-cut leather sections. They sew them together to make what's called the skull of the helmet. This piece will become the brim of the helmet. To give the skull structure, a worker folds and sews each section, then flattens the crease with a special hammer. He uses a template to score a sewing line in the leather. Then he uses a powerful sewing machine to join the sections together. He now joins the 2 halves together, reinforcing them with double stitching. The resulting 8 ridges give the skull stiffness and strength. He stretches the leather over a plastic mold and trims excess leather from the ridges. Then he clamps 4 vice grips to the rim. These attach to a hydraulic jack that stretches the skull overnight. After applying glue to the ridges, he runs them through compression rollers for a tight bond. They wet the brim piece several times to make it more pliable. Then they stamp it with the design used by this company since 1846. But first, a worker inserts a wire that will give the brim some structural support. Then a temporary plastic cover and a lid to ensure an even spread of pressure across the brim. She stuffs the edges of the leather inside before the press applies 10 tons of force to imprint the design. Next, a worker sews the skull to the brim. He removes the excess leather at the base of the skull and cuts out the center of the brim. Then he removes the plastic mold. To seal the leather, they dip the hats in a vat of hot rosin, a type of tree sap. After 55 minutes, they remove them and let them dry at room temperature for 8 weeks. This slow-drying process makes the leather about as hard as wood. Drying it mechanically would make it brittle. Now for the inside. They insert a plastic cap to reinforce the structure. The fit is intentionally tight, so they use a mallet to tap it into place. Inside that, they add another plastic cap with nylon straps to resist the impact of falling objects. Here, a worker uses an acetylene torch to burn off any loose threads and soften the leather in order to bend the brim and straighten the ridges later on. Turning up the sides is basically for aesthetics, but the longer edge in the back is to direct water away from the neck. After adding a synthetic fire retardant liner, he sands the outer surface to prep it for painting. First, a fire retardant chemical primer. Then they use a semi-gloss latex paint in firefighter's black or white for the chief. Or if you prefer, a clear varnish to show off the natural leather. Add a front piece with the firefighter's signature brass eagle on top, and some fluorescent stickers for extra visibility. And you've got the right headgear for a hero's job.
Fire hydrants have been in use for more than 200 years. In the old days, their main purpose was to supply water to fight fires, but they also provided the public with a handy water supply. Today, fire crews rely on the nearest hydrant to help them douse flames whenever and wherever they break out. Fire hydrants are essential to every community. They need to be instantly recognizable, easily accessible, and simple to operate. The ones in residential areas are designed to deliver an impressive 1,500 gallons a minute. The hydrant making process starts with recycled scrap iron, along with steel and raw iron. Using a magnetic crane, workers load the metals into a furnace and melt them at 2,800 degrees Fahrenheit. This turns the scrap metal into molten iron. This super hot mixture is transferred into a remote-controlled ladle and emptied into an automated pouring system. To cast the hydrants, workers first make two-part molds by compressing a mixture of sand and bonding materials. One part, called the mold, forms the hydrant's exterior shape, while the other part, called the core, forms the interior shape. An automatic core setter positions a core in each mold. Then, a conveyor advances the mold under the pouring box, which fills the cavity between the mold and core with molten iron. After the iron cools and solidifies, the molds enter a tumbling barrel. As they revolve, the sand gradually disintegrates, freeing the iron casting inside. Workers drill and thread the hydrant castings to prepare them for assembly. Then they pre-assemble and paint them. The fire hydrant's internal workings, called the valve assembly, allow water to flow through when the hydrant's open. A series of rubber O-rings on the main valve will prevent leaks when the hydrant's closed. Now, the hydrant is ready for final assembly. Workers attach the nozzle section to the top of the hydrant barrel and fasten nozzle cap chains with a crimping tool. Using a torque wrench, they attach cast iron safety rings. These rings are designed to disengage the top from the bottom of the hydrant so it doesn't get damaged if a vehicle hits it. Workers clamp the water main connector into place and pressurize the hydrant to normal city pressure to check for leaks. Using a hoist, they lower the pre-assembled nozzle section over the stem and fasten it to the water main connector with stainless steel bolts. They lower the bonnet into place, bolt it to the nozzle section, then open the hydrant for a high-pressure test. They turn the operating nut to allow water to flow through. But first, they have to force out the air inside the hydrant with water. Workers transfer the finished hydrant to a pallet and apply final paint touch-ups. Some fire hydrants that were installed more than 100 years ago are still in use today. The first fire extinguisher on record was built in Europe in the Middle Ages. It worked like a giant syringe that squirted water at a fire. The modern extinguisher uses compressed air as a propellant and douses the fire with flame-retardant liquid, powder, or foam. Squeezing the lever opens a valve that releases compressed air. The pressure then propels the chemical through the hose and out the nozzle. Production of the release valve starts with cylindrical pieces of aluminum called blanks. A carousel runs each one through 16 different machining stations. At each stop, under a shower of lubricant, tools shape the blank for 6.5 seconds. As each blank completes the circuit, it comes off the carousel. From blank to valve in 1.25 minutes. Now, the fire extinguisher's aluminum handle is riveted onto the valve. It pivots on a pin. Next, an aluminum lever is riveted onto the handle. This is the lever you squeeze to use the fire extinguisher. Then comes the valve stem, the valve's inner workings. Workers simply place it inside, and an automated assembly machine does the rest. It positions a spring over the stem to create resistance when you squeeze the lever. Then comes a retainer to hold both the stem and spring in position. Now, workers slip on a plastic thimble to position the rubber O-ring that goes on next. The O-ring acts as a seal between the valve and cylinder so nothing leaks out. The siphon tube runs from the valve down into the cylinder. The firefighting chemical goes up this tube, then out the nozzle. The compressed air inside the cylinder is what propels the chemical. This gauge shows if there's sufficient pressure for that to happen. After coating the gauge's threaded stem with sealant to prevent leaks, a worker screws it onto the valve. The valve unit is now fully assembled, tested, and ready for installation on top of the cylinder. To attach it, the cylinder needs a threaded collar. With the help of a press, a worker positions it. The cylinder also needs a bottom. The technique this factory uses to fuse the bottom and collar is called brazing. It's similar to soldering, but with a copper ring as a bonding metal. After positioning a brazing ring at the base of the open cylinder, a steel bottom is pressed into place. Then, workers position a brazing ring over the collar. Now into a brazing furnace for 1 hour and 45 minutes. The 2,000-degree heat melts the two copper rings, bonding the parts they connect. Next stop, the static paint booth, where workers apply a positive electrical charge to the paint particles and a negative charge to the cylinders. This draws the paint onto the surface evenly. Then, it's into an oven for 45 minutes to bake the paint. Once the cylinders cool, automated machinery fills them with a fire-extinguishing powder. The main ingredient is a form of ammonia. When it's sprayed on a fire, the heat melts the particles of powder, fusing them into an oxygen-blocking blanket that smothers the flames. After the cylinders are filled, an automated machine screws a valve onto the collar of each one. Now it's time to pressurize the cylinder. The lever is squeezed to open the valve, enabling a compressor to fill the cylinder with air. They keep filling until the air pressure reaches 13 bars, about 6 times the pressure in a car tire. Next, workers screw on the nozzle and install a locking pin. This immobilizes the lever so the extinguisher can't discharge accidentally. As the instruction sticker says, in case of fire, you just pull the pin, aim, and spray. This mounting bracket lets you hang the fire extinguisher in an accessible spot so it's close at hand if you need it.
The jaws of life were first used in 1963 to free race car drivers from car crashes. It was so big it had to be suspended from the back of a pickup truck. Today it weighs as little as 33 pounds and is small enough for one person to operate. It can free an accident victim from a car in minutes. In an emergency situation, timing is everything. A rescue tool has to pry open a vehicle as easily as a tin can or cut through solid steel like butter, because a few seconds can make all the difference. What gives the cutting blades and the spreading arms their power is hydraulic fluid. The jaws of life begin with the milling machine that shapes the spreader arms from a bar of solid aircraft-grade aluminum. The spreader arms then get a protective coating. A lathe now makes the cap that fits on the end of the tool. A high-speed carbide tip shapes the solid aluminum into a finished end cap that is then drilled and treated to a coat of rust-resistant protection. Arms that both cut and spread are made from tool steel. A surface grinder ensures that the two arms are perfectly flat. A worker installs a seal that prevents the hydraulic fluid from leaking out of the cylinder. He lubricates a piston with hydraulic fluid so it slides into the cylinder without damaging the interior. Then he taps it in so it will connect with a link assembly. He attaches a link assembly to the piston and secures it in place. The link assembly relays power to the cutting blades or spreader arms. He then attaches an assembled end cap to the cylinder and bolts it in place. He connects the two hoses that lead to the tool's hydraulic cylinder. He puts on a hand grip that protects the hoses and makes it easier to work the thumb wheel. He tightens the bolts and completes the control valve. He then attaches the front handle that allows the operator to hold the tool safely. This protective guard will keep all the moving components away from a rescuer's hands. Then he aligns the holes in the blades to the tool and inserts a steel pivot pin. He puts on a lock nut, and as with all fasteners on the rescue tool, he tightens it to a precise engineering specification. After mounting the blades, he secures them to the link assembly with a steel alloy pin and a snap ring. Then he folds the protective guard back and finishes assembling the tool. A worker then tests the tool, which has been filled with fire-resistant hydraulic fluid. The fixture he uses is designed to measure the pressure at the strongest point in the cutting. The tool passes the pressure test. Whether it's a rescue tool that cuts through metal or pries it open, emergency response teams arriving on an accident scene will have what it takes to help save lives.